Hello everyone, thank you for taking a look at the essay talk about the paper A1 minus 1 over E minus epsilon approximation for the monotone submodular multiple knapsack problem. My name is Ariel Kulik. This is a joint work with Yaron Feilstein, Sefi Naor, Dani Raz, and Adas Shachnai. All of us are from the computer science department at Technion. So the first thing we need to do is to define the problem. And in order to define the problem, we first need to discuss submodular functions. So we let I be some finite set of items, and we let f be a function from subsets of items to the reals. Now, we define the marginal value of an item I with respect to a subset S of items by f of S and I minus f of S. That is, it's in some sense the added value from adding the item I to the set S. Now, we say f is submodular if for any subsets S and T such that S is a subset of T and an item I which is not in T, it holds that the marginal value of I with respect to the set S, the smaller set, is at least the marginal value of the item I with respect to T, the larger set. In some sense, this means that as the set S grows bigger, the marginal value of the item I gets smaller. Now, while not all submodular functions are monotone, in this work we focus on monotone submodular functions. So f is monotone if for any subsets of items S and T such that S is a subset of T, it's also that f of T is at least f of S. And now submodular functions arise naturally in many settings. Classic examples are coverage functions, which are monotone, and cuts in graphs, which are not monotone. Now, we can now define the monotone submodular multiple knapsack problem, or in short, SMKP. So the input for the problem is a set I of n items, where item I has a weight wi. The input also consists of a set B of m bins, such that each bin B has capacity WB. Now, the number of bins is part of the input. It's important to mention that. Also, we're given a monotone submodular non-negative function f from the subsets of items to the non-negative reals, and the function is given to us via an oracle. We define a feasible assignment, or just an assignment, as a mapping from the bins to subsets of items. Essentially, we assign a subset of items to each of the bins, and we require that the total weight of items assigned to each of the bins is at most the capacity of that specific bin. Our objective is to find some assignment A such that the value f of all the items which are assigned to some bin is maximal. So let's take an example. So here we have 4 items, 1, 2, 3, and 4, and 2 bins, B1 and B2. And we can consider an assignment. We can consider an assignment in which the third element is assigned to the first bin, and the first and second items are assigned to the second bin. And you can verify that this is indeed a feasible assignment, that it satisfies the capacity constraint. And the value of the assignment is the value f over the sets of items which are assigned to some bin. And in this specific case, it is f of 1, 2, and 3, the items which are assigned. So the problem is a generalization classic problem. So if we take f to be multiple knapsack problem for which there is no polynomial time approximation scheme, and there is no fully polynomial time approximation scheme, was later improved to an efficient polynomial time approximation scheme. Also, if we take m to be 1, that is, we have only a single bin, what we get is monotone submodular maximization with a single knapsack constraint, for which there is a simple 1 minus 1 over approximation, our monotone submodular multiple knapsack problem for any epsilon greater than 0. And this result is nearly optimal. That is, there is no 1 minus 1 over e plus epsilon approximation without any assumption in the oracle model, and also under p not equals in p for the special case of coverage functions. So what was known about the problem? So if the number of bins is constant, you can derive a variation of the algorithm of Sviridenko, which yields 1 minus 1 over e approximation. And this is not very hard to do. Also, very recently, Sung, Zhang, and Zhang provided a deterministic greedy-based 1 minus 1 over e minus epsilon approximation for the special case of uniform bin capacity. They also provided a randomized 1 minus 1 over e minus epsilon approximation for some restricted input class. And the work was conducted simultaneously and independently of ours. So let's discuss the algorithm. So we will describe the algorithm in several phases or steps. So at first, we will present a solution for the case of uniform bin capacities, and then we will extend it to arbitrary bin capacities. And for this extension, we will define blocks and n-leveled instances, and n-leveled instances are in some sense easy instances. And then we will show how to convert a general instance to an n-leveled instance. So we start with uniform bin capacities. So what we assume now is that the capacity of all the bins is exactly 1, and that the number of bins m is large. And this allows us to create a classification of the items into small and large items. So we fix some u greater than 0, and we say an item I is large if its weight is more than u. Otherwise, we say the item is small. And we define a configuration as a subset of large items which fits into a single bin. That is, their total weight, and the total weight of the items in C is at most 1. So a configuration can have at most 1 over mu items in it. Therefore, the number of configurations is at most n to the power of 1 over mu, and this number is polynomial. Now, we use this classification into large and small items and the definition of configurations to define a new set E of subsets of items. So the items or elements in E are subsets T of items, which are either a configuration or a set which contains a single small item. Now, following the previous argument, what we have is that the number of subsets in E is polynomial in the input. And we use E to define a new function, which will be some alternative objective functions, a function we will use. We refer to it as G, from subsets of E to the non-negative reals. And G of D is defined by F of all the items which appear in some subset in B. And it can be easily shown that G is monotone, submodular, and non-negative. Now, we use the function G and the set E to define a new problem, to which we refer as the block constraint problem. In the block constraint problem, what we are trying to do is to maximize G of D subject to 2 constraints. The first constraint is that the number of configurations in D is at most m. This reflects the intuitions that we need only 1 configuration per bin. Recall that m is the number of bins we have. The second constraint is that the total weight of subsets in D is at most m. Now here, m is actually the total capacity of the bins, because we assume the capacity of each bin is exactly 1. Now, it's easy to show that the optimum to the block constraint problem is at least the optimum for the submodular multiple knapsack instance we're handling. The problem itself is an instance of monotone submodular maximization with a two-dimensional knapsack constraint, for which there is a 1 minus 1 over E minus epsilon approximation. The second direction also holds, that is, we can convert the solution D for the block constraint problem to an assignment A for the instance, such that the value of A, f of all the items which are assigned to some bin, is at least 1 minus 1 over m minus 2 mu g of d. And assuming m is large and mu is small, it is roughly g of d. And the way we obtain this conversion is by assigning a configuration to each bin. Now, there are at most m configurations, therefore we need at most m bins. Then we use first fit to assign the small items to bins. This may require some additional bins, but we can bound the number of required additional bins. And then we simply discard the least profitable bins. And this can incur some value loss, but not a significant value loss. And this is how we get this conversion. And using the block constraint problem and this conversion, we get an algorithm for the case of uniform bin capacities. So what we do is we find an approximate solution for the block constraint problem. So what we have is that the value of the solution we get is at least 1 minus 1 over E minus epsilon, the optimal solution for the SMKP, for the submodular multiple knapsack instance we're handling, because the optimum for the block constraint problem is at least the optimum for the submodular multiple knapsack instance we're handling. And then we convert the solution D to an assignment A. And then we have that f of all the items which are assigned in A is at least 1 minus 1 over E minus epsilon minus 1 over m minus 2 times mu, the optimum. And this value is arbitrarily close to 1 minus 1 over E. So now that we have a solution for uniform bin capacity, what we need to do is to extend it to arbitrary capacities. And the central definition here is the definition of block. So a block is a subset of bins which all have the same capacity. So let's take an example. We have here some bins, and the first 4 bins all have the same capacity, therefore they form a block. Also, the next 2 bins have the same capacity, so they also form a block. And basically, if the instance has a uniform bin capacity, then what we have is that the set B is a block itself. And for this specific case, we found a reduction to submodular optimization with a 2-dimensional knapsack constraint. And this can be actually generalized to an arbitrary number of blocks. So what we can do is that if B has a partition to blocks K0 to KL, then we can reduce the problem to monotone submodular maximization with a D-dimensional knapsack constraint, where D is twice the number of blocks, or 2L plus 1. And this is done essentially in the same way we handled uniform bin capacity, so it's a bit more technically involved. And we essentially convert each block into a 2-dimensional knapsack constraint. However, there is no constant approximation for monotone submodular maximization with a D-dimensional knapsack constraint if D is not a constant. However, the instances we get from this reduction are not generic. So if we look into the algorithm for monotone submodular maximization with D-dimensional knapsack constraint, what we can observe is that blocks which have large number of bins, which have many bins, are easier to handle. And what we can show under some additional technical condition we ignore here is that if we only restrict our attention to instances in which the number of bins in the jth block is aj for some fixed sequence of numbers aj, such that aj grows faster than j, then we can get an approximation ratio which is arbitrarily close to 1 minus 1 over e. Therefore, our objective becomes to convert a general instance to an instance which have some good partition into blocks. And The structure we use is n-leveled instances. So we say an instance is n-leveled if the set B of bins can be partitioned into blocks k0 to kl, such that the number of bins in the jth block is n to the power of j over n squared rounded down. So let's try to make some sense of this scary formula. So the first n squared blocks have 1 bin each. Then the next n squared blocks have n bins each. And the following n squared blocks have n squared bins each, and so on. So for each of these n squared blocks, we refer to them as a level. So this is level 0, level 1, level 2. And all the blocks in the same level have the same number of bins. And what we also have is that the number of bins per block grows exponentially with the levels. And due to the previous argument, we can, in practice, find an approximation ratio arbitrarily close to 1 minus 1 over e for n-leveled instances. So what we really need to do now is to show how we can convert a general instance to an n-leveled instance. And the main tool we use in this conversion is grouping or shifting, a technique commonly used for bin packing problems. So we want to take an instance and convert it to be an n-leveled. So we do it through a series of steps. So the first step is to sort the bins according to their capacity. We then group the bins into blocks in some sense. And the way we do it is that we actually know the target size of each block. We know the size of the first block, we know the size of the second block, we know how many bins we want to have in each block. So what we do is simply assign bins consecutively to a block until we reach its target size. And once we reach the target size of the block, we simply continue to assign bins, to the next block. So here we have an example with n equals to 2. And in this example, the first 4 blocks have 1 bin each. So we can see that we assign the first bin to the first block, the second bin to the second block, and so on. And then we have an additional 4 blocks with 2 bins each. So we have 2 bins assigned to K4 and another 2 bins assigned to K5, and so on. Now, those are not actually blocks because we just group together bins, but they don't have the same capacity. So what we do now in the third step, we reduce the capacity of the bins to form a block. And the way we do it is that we reduce the capacity of each bin to the minimal capacity of a bin in that block. So here, for example, we decrease the capacity of the first bin in K4 to be the capacity of the second bin in K4. And here, for example, in K8, we reduce the capacity of the 3 bins, the first 3 bins, to be the capacity of the last bin. Now, following this conversion, what we have is an n-leveled instance. And since we only reduced capacity of bins, it's easy to see that if we have a solution with the new capacities, which satisfies the capacity constraint with the new capacity, it's also a solution for the original instance with the same value. What we're going to show is that the opposite direction also holds up to a small loss in the value. If we get a solution to the original instance, then it can be converted to a solution with the new capacity while maintaining 1 minus 1 over n of the value. And the crucial observation here is that if you look at the new capacity of the bins in some block kj, then it is at least the original capacity of bins in kj plus 1 in the subsequent blocks. And the reason for that is that the new capacity of bins in kj is the capacity of the last block, of the last bin in kj, because the bins were sorted according to their capacity, which is at least the original capacity of all the bins in the consecutive blocks. So let's see how we can do this conversion. So we have some solution to the original instance, and we're going to perform 2 steps. So on the first step, we're going to empty the n least profitable blocks from each level. Now recall that each level has n square blocks, so we are essentially vacating 1 over n of the blocks in each layer, in each level, sorry. And what we show in the paper is that we can actually assume that the blocks we empty are the n last block in each level. Then we do a shifting technique to ensure the capacity constraints hold. So what we do is we take the first block from each level and move the content of its bins to the empty blocks from the previous level. So here, for example, we can look at the first block at level j+1, and we move the content of its bins to the empty blocks, to the bins of the empty blocks at level j. Now, there are n to the power of j+1 bins at the first block of level j, and also the empty blocks at level j contain n blocks with n to the power of j bins each. So the number of bins of the source and of the target of this shifting is the same, so we can perform it. Also, for any other blocks, that is a block which is not the first on its layer, we just shift the content of its bins to the bins of the previous block on the same layer. And because blocks on the same layer have the same number of bins, we can perform this operation. Now, following the shifting, what we have is that the assignments to each block are the original assignment for a later block. And by the property we described on the previous slide, we get a feasible assignment with respect to the new capacities. And what's important to note is that on the first step, when we empty the bin, we only lost 1 over n of the value of the solution. So what we obtained is that a solution to the n-level instance with 1 minus 1 over n of the value of the original solution. And this means that if we convert an instance to an n-level instance, the optimal value for that instance only decreased by 1 over n. It's only a small decrease in the value of the optimum. And using these tools, we can derive an algorithm for submodular optimization with a multiple knapsack constraint. And the way we do it is by guessing a constant number of items and their assignment to an optimal solution. This is definitely required for actually solving the block constraint problem for n-leveled instances. Then we convert the instance to an n-leveled instance. This might decrease the optimum but only by a bit. Then we solve the block constraint problem, and we get an approximation ratio which is arbitrarily close to 1 minus 1 over e. And we convert this solution for the block constraint problem to a solution for the original instance, for the submodular multiple knapsack instance. And overall, what we get is an approximation ratio which is arbitrarily close to 1 minus 1 over e. So we presented a solution for the monotone submodular multiple knapsacks problem. And it's natural to ask whether the solution we proposed actually works for the non-monotone case. That is the case where the function f is a submodular but not necessarily monotone function. And the technique we presented does not work in this case. And one of the main obstacles is that we changed the function f to a new function. We converted it into a function g, which is defined over subsets of items. And it is defined by g of d equals to f of all the items which appear in some set of d. Now, while it's true that if f is monotone and submodular, then g is also monotone and submodular. If f is a non-monotone submodular function, then g may not even be a submodular function. And our technique simply does not work in this case. So we looked for a way to solve the problem without changing the objective function. And we actually found one. And the solution we found was very generic and scalable. We were able to solve many other problems utilizing this new solution. And this result appears in the paper Tight Approximations for Modular and Submodular Optimization with the Resource Multiple Knapsack Constraint. and it's currently available on the archive. So I want to thank everyone who stayed with us until the end. You're more than welcome to come and visit us at the ESA poster session, and also we will be very happy if you will take a look at the paper itself. Thank you.